This is section 2.6, which is rational functions. There are 3 AP Precalculus standards that are associated with this section. 1.7, which is rational functions and end behavior. 1.8, which is rational functions and zeros. And 1.9, which is rational functions and vertical asymptotes. So there's a lot of stuff in this section. So to start out with the definition of a rational function, r of x is equal to f of x over g of x, where f and g are polynomials. So basically anytime you have a polynomial in the numerator and a polynomial in the denominator, that makes a rational function. So to start with, we're going to talk about kind of the format of a rational function when we're talking about transformations. So just like our normal a, h, and k, these do the same thing, with a being a vertical stretch or shrink, h moving it to the left or right, and k moving it up or down. So for example, on this first one, if I have it written just like this, I know that this would be a vertical stretch, and the x plus 3 would mean that this is going to be shifted to the left 3. Okay, sometimes you're going to have a function that it's not easy to see those transformations, like the bottom one. So what you can do in that case is you can divide. You can take the numerator divided by the denominator. So if we do a little long division here, we can take 3x minus 7 divided by x minus 2. So x goes into 3x 3 times. 3 times x is 3x. 3 times negative 2 is negative 6. We're going to subtract. So negative 7 minus a negative 6 is really plus 6. So I get negative 1. So that means that we have 3 plus negative 1 over x minus 2, our divisor. And so another way to think about this is to, it's h of x, not f. Let's fix that. Okay, so h of x is equal to, if I flip these around and write negative 1 over x minus 2 plus 3, then it's in the form that we see up here with our transformations. So this would tell me that it is a reflection across the x-axis because of that negative 1. This would tell me it's shifted to the right 2, and this would tell me it's shifted up 3. So again, when it's in a form that we can't really tell, we can always divide the numerator by the denominator so we can clearly see those transformations. Okay, so here is a list of all of our key features and how we find them. So to start out with, the x-intercepts are going to be whatever numbers make the numerator equal 0. So if I set it equal to 0 and solve, those are my x-intercepts. My y-intercept is what I get when I plug in 0 for all the x's. My vertical asymptote, or asymptotes, we could have more than one, are what values make the denominator equal to 0. The horizontal asymptote, which we can also call the end behavior asymptote, we're going to find that by comparing the degree of the numerator and the degree of the denominator. If we have a slant or oblique end behavior asymptote, that is when the degree of the numerator is 1 more than the degree of the denominator. We can't have both of these at the same time. So you're either going to have a horizontal asymptote or you could have a slant or oblique asymptote, but both can't occur at the same time. And then holes or removable discontinuities are any canceled factors that we have. Okay, so we're going to graph and go through the whole process of 2 of these examples. So our first example, what we want to do before we start anything is we want to factor if we can. So if we look at this one, we can see that the numerator is a quadratic. So we can say what multiplies to negative 3 and adds to 2. That would be x minus 1 and x plus 3. And in the denominator, we have 2 terms and they both have an x. So I'm going to factor out an x, which gives me x plus 3. So right off the bat, we can see that we have an x plus 3 that's going to cancel, which tells me that there is a hole at x equals negative 3. So I'm going to keep that in mind when I'm graphing this. Okay, so the first thing is the x-intercept. So the x-intercept, what we talked about on our previous previous example is what makes the numerator equal 0. I'm looking at my simplified x minus 1 over x because the whole has already been removed. We're going to take that out. So that would mean that my numerator is just x minus 1. So what number would make x minus 1 equal 0? That would be 1. So my x-intercept is at the point 1, 0. Okay, my y-intercept, if I plug in 0 for both of the x's, 0 minus 1 would be negative 1 over 0, which I can't do. So that means that I don't have a y-intercept. So if it causes it to be undefined, it means I don't have it. Okay, my vertical asymptote, that is what makes the denominator equal 0. So I am not looking at my whole because the whole has already been removed. So we're just looking at what's left. So we have just an x in the denominator. So the only number that could make x equal 0 is 0. So that means that x equals 0 is my vertical asymptote, and also explains why I don't have a y-intercept. So if I have a vertical asymptote on the y-axis, it's not going to touch the y-axis. Okay, my horizontal asymptote. I'm going to go back to the original here, and we're looking at the biggest power of x. We actually could look at the simplified answer too. But my biggest power of x is x squared. I have 1x squared on the top, and I have 1x squared on the bottom. So that's what I mean by compare. I have 1 divided by 1, which means y equals 1 is my horizontal asymptote. And we said that we have a whole at x equals negative 3. Okay, so I'm going to start with my asymptotes. So my vertical asymptote is at x equals 0. So that's right there. My horizontal asymptote is at y equals 1. I'm going to plot a point, my x-intercept at 1, 0. Okay, and then that's all I have. So other than I know there's a hole. So what I would do is I would go to your graphing calculator and I would type the function in, and then use the table feature so that I can find a couple more points. So from my calculator, use the table, I'm going to look at to the left and to the right of my asymptote. So I'm going to start with negative 4. I get the point 5/4. Negative 2, I get the point 3/2. Negative 1, I get the point 2. 2, 1/2, and 3, 2/3. Okay. So the other thing I'm going to do is I'm going to figure out what the value of the whole is. So we know we have a whole at negative 3, but we think about what would we get if we plugged in negative 3 to my simplified thing. So I get negative 3 minus 1 divided by negative 3. So that would be negative 4 over negative 3, or 4/3. So my whole is at negative 3 4/3. So I'm going to draw that in there first. So negative 3 4/3 would be 1 1/3. It's kind of hard to pinpoint on this graph, but I'm going to draw an open circle there so we know that that's our whole. So at negative 4, we're at 5 1/4, negative 2, 1 1/2, negative 1, 2. So we can kind of see on this side of my graph, we have that. And then over here we have 2, 1/2, 3, 2/3. So we can kind of see that's that half of the graph. Okay, so those are all those key features and how we find them. Okay, let's look at our next and final example. Okay, so same thing on this one. I want to factor if I can. The top is a numerator, the numerator is a quadratic, is what I meant to say. What multiplies to negative 10 and adds to negative 3 would be negative 5 and 2. And the denominator is just x plus 3. We can't do anything with that. So I factored it to see if I have any holes or if anything cancels, and it doesn't in this case, and that's okay. So to start with, my x-intercepts are going to be what makes the numerator equal 0. In this case, we have 2. We have one at 5, 0, and negative 2, 0. My y-intercept would be if I cover up, so I actually just think about what would I get if I cover those up. I would get negative 10 over 3. I'm going to erase that so we can still see. So negative 10 thirds is my y-intercept. So I can write it as 0, negative 10 thirds. If we're putting it on a graph, it might be easier to write it as a mixed number. So 0, negative 3 1/3. But either way. Okay, my vertical asymptote. So that is what makes the denominator equal 0. So that would be negative 3. My horizontal asymptote is our biggest power of x. So we have 1x squared on the top, and we don't have any x squareds on the bottom. So we have 1x squared over 0x squared, which is not possible. So that means we do not have a horizontal asymptote. So then we talk about a slant asymptote occurs when the degree of the numerator is 1 more than the degree of the denominator. So in this case, we are going to have a slant. And we find that slant by dividing. So I can do synthetic division on this one because the denominator is linear. So I'm going to put 1, negative 3, negative 10. I'm going to put negative 3 because that's what makes my x plus 3 equals 0. So this would be 1. 1 times negative 3 is negative 3, negative 6, 18, and 8. And this is one time that actually we don't need to worry about the remainder. So we just put the first two parts tells us the equation of our slant asymptote. So this would be 1x, or just x, minus 6. So that's the equation of our slant asymptote. Okay, so let's go ahead and put all this on here now. So vertical asymptote at negative 3. Slant asymptote at y equals x minus 6. So that means I go to negative 6, and my slope is up 1 over 1. And I'm noticing that my y-axis of my graph is going by 2's. Okay. So this is not the easiest to draw, but there we go. There's my slant asymptote. Okay, and now I need some points on my graph. Okay, so I have an x-intercept at 5, 0. I have an x-intercept at negative 2, 0. I have a y-intercept at 0, negative 3 1/3. It's probably going to be right about there. And that's all I know. So that actually is probably enough to sketch this side of the graph. Okay, but I also need to know what's happening to the left of my vertical asymptote. So I might plug in some values into the table on my graph, and I would get negative 4, negative 18, and negative 5, negative 15. So I'm going to plot those. Negative 4, negative 18, and negative, oh, that was negative 5. Let's try that again. Negative 4, negative 18, negative 5, and negative 15. Okay, so that kind of shows that half of the graph. So that's what that one would look like, and how you handle slant asymptotes.